Do I just start? Okay, this is the joint work of me, René, Rydhof, my supervisors, and then Bøgsted, also my supervisor, and then Léon Gondelman. So for most of the stuff that we'll be looking at today is stuff that was put forward by Haidberg and Prasad in their two seminal papers on the subject. If something has not been formalized, it will be pointed out in the slides. So kind of to explain the situation or the problem at hand, we have two organizations that wish to communicate, and each will use a security lattice for modeling information flow within that organization. So what this means is that we have a finite inhabited lattice, and then we will label information with elements of this lattice, and then members of an organization will get a clearance, which is also a label, or an element of the lattice. So for example, I can have the label Intel, and then I will be able to read information of that is labeled Intel, but also public. So essentially, information is allowed to flow upwards through the lattice. The problem at hand is then that we have two organizations and they wish to communicate. So normally we would just take the product lattice and then label everything with two labels and give everyone two clearance levels. But kind of the approach that we will consider is that we will define a translation or a map that is an order preserving function between the two lattices. And then this lattice will be kind of a specification for how we translate the labels, but it can also be seen as kind of a specification for communication. So essentially, information allowed to flow through the lattice and via the connection, but also via the transitive closure of this. Of course, we need a translation the other way for communication to happen, but in doing so, we might introduce insecure flows. So here we have allowed information to flow from nuclear to Intel, and this breaches the compartmentalization of AF. So kind of to make this problem go away, we enforce what we call LC1 and LC2. Colloquially, we refer to this as security. And what they say is that the composition of the functions going each way must be non-decreasing. Informally, this kind of means that an organization cannot observe their own policy being broken, or said otherwise, by sending information back and forth, we can accidentally declassify it. And in essence, this is the Lagois connection. So it's a stupid play on words on the Lagois insertion, or Lagois connection, sorry. And it is a generalization of the Lagois insertion. So there's also LC3 and LC4, but like for the presentation I'm going to give today, they are not really relevant because we only really care about security. So what Haidberg and Prasad do is they attach an operational model, and then they provide a type system for that operational model, and then they can prove that the type system is secure, and the soundness, the type system basically enforces what we call non-interference. So the type system, the operational model is somewhat uninteresting because what they assume is that you have basically two transactional languages, one for each organization, and then the programs that we consider are just basically transactions interleaved with communication between the two organizations. So in effect, this is just a piece of straight line code with a fancy assignment. This is something we are trying to move away from by basically actually considering two separate programs that are running on their own and communicating non-deterministically. Yes, kind of one of the big differences between their informal work and our formal work is kind of they are very informal in the assumptions that they put on the two underlying transactional languages, C and C prime. And here we provide a formal interface where we can basically query elements of that type for the information that we need. The type system then assumes that there is a Lagois connection, and then for two labeling functions, one for each organization, it basically, most importantly, checks that the Lagois connection is satisfied. So if we want to send information from a variable x to a variable y, we have to check that the label of x carried over the Lagois connection is less than the label of y. And that is in essence kind of how we ensure security between the two organizations. We can then formalize, of course, their soundness results, which says that if we have an attacker at corresponding levels at each lattice, and that we can type a program, then if the initial state is observably equal to the attacker, then it will also be observably equal after execution. So basically, the attacker will never learn anything from observing execution. So that was some stuff by Bhartman and Prasad, and now kind of what we've been working on is that often you don't consider communication just between two systems in isolation, but between an arbitrary amount of organizations. So we could imagine that a third party wants to join in. But we have this result from Milton, which says that if we have two Lagois connections and we compose them, then the result is also a Lagois connection if this condition holds. But we can do one better, and then if we have two posit systems and that they are both secure, then the composition will also be secure. So we can slap together Lagois connections to have secure communication between an arbitrary amount of organizations. But in doing so, we have kind of created a new problem, because in this case, we could imagine that EA and NC wants to exchange secrets. But at the moment, their secrets are being thrown in the bin over at AF. So they can't actually send secrets to each other. And the solution we consider is that we just bypass the intermediary condition. Oh, sorry. Also, changing the order around doesn't fix the problem, because now AF cannot communicate their nuclear secrets with NC, which they could before. And then, of course, the solution is just to bypass the intermediary. And this kind of leads us to study arbitrary graphs of an arbitrary number of organizations. So we have a graph, and each node is basically labeled with the lattice, and we label each edge in the graph with the corresponding Lagois connection. And then the question is to ask, is the graph secure? And we know from Flemming Nielsen and René Rydhof Hansen's work that we can determine basically the security of such networks in cubic time. But in our work, we've been interested in determining if we can just look at the structure of the graph alone and then derive security without looking at the underlying connections. And what we've been able to show is that if it doesn't really matter which way you send information, in a sense, if all paths that information can take behave the same, then the graph is secure. And then as a corollary to this fact, if the graph is a forest, then it's also secure. But we are kind of not solving a problem, because either it doesn't matter which way you send information through the graph, or there's only one way, and thus we have to pass our information through an intermediary. Yes. So to solve this, we are considering that we can show this result, where we have essentially, if we have two graphs, we can connect them by a single Lagois connection, and then if these two graphs are secure, this total graph is secure. At the moment, this has not been formalized, but we are working towards it. And what this allows us to do is that we can locally bypass intermediaries and then connect these local networks in a forest, essentially. And then this forest is also going to be secure. So to conclude, we have some future works. So I talked a bit about that we are trying to move away from the original model presented by Hardwire and Passat. And with respect to that, we are working on a soundness proof of our own operational model. And then one thing that we are starting to consider is that if how we would model organizations moving around, but also changing their policies. Essentially, we are planning to use certain transformations between these graphs. Yes.